Here's a question worth sitting with. If artificial intelligence has been crushing benchmarks left and right, winning at Go, solving Olympiad math, beating competitive programmers, why hasn't this translated into measurable economic transformation across professions like finance, law, manufacturing, or architecture? The authors of Agent's Last Exam argue this isn't a capability gap so much as an evaluation gap. The benchmarks we use to measure progress simply don't reflect the kind of long, messy, software-intensive work that actually constitutes professional labor. And because benchmarks shape research priorities, what gets measured gets optimized, and what doesn't get measured tends to stagnate. To understand why this matters, consider how prior benchmarks slice up the problem. On one end, you have static question-answering tests like MMLU or GPQA that measure what a model knows, but not what it can do. In the middle, agentic benchmarks like SWE-bench or OS World test multi-step tool use, but only in narrow software-centric domains, usually with curator-invented tasks, rather than real workflows. At the project scale end, benchmarks like GDP-Val and the Remote Labor Index do test economically grounded deliverables, but they rely on expensive human grading and still cover only a small slice of the labor market. Each existing benchmark trades away at least one of three things: realism, breadth, or verifiability. Agent's Last Exam, or ALE, is an attempt to hold all three at once. The scope here is ambitious. Working with over 250 industry experts, the authors built a taxonomy grounded in the U.S. Federal Occupational Classification, which they call SOC 2018, combined with the ONET occupational database. They clustered software-mediated occupations into 13 industry domains, spanning 55 subdomains, covering everything from chip sign-off routing to molecular docking to character sculpting to weather forecasting. The result is roughly 1,490 task instances drawn from projects that domain professionals have actually completed, things that took experts days or weeks of real work. Think of it less like a test and more like an apprenticeship portfolio. Each task is something a working professional has already shipped, not a contrived scenario. The construction pipeline is worth understanding because it explains why the tasks have a different character than typical benchmark items. Experts submit past projects through a portal where AI-assisted tools help them refine the specification into 5 pieces: a natural language description, the input files, the target software, the expected deliverable, and the evaluation criteria. Then submissions go through a conference-style review process with verdicts like major revision, minor revision, borderline accept, and strong accept. Engineers then convert accepted specifications into runnable assets with provisioned software containers and codified evaluation logic. Finally, a peer review committee checks that the reference output is correct and that the evaluation bounds are neither impossibly narrow nor too permissive. To prevent contamination, only about 10% of tasks are released publicly, with the rest held private and rotated over time. Now to the technical heart of the work, which is how you verify heterogeneous deliverables without falling back on human judgment. A correct output might be a KD file, a spreadsheet, a 3D mesh, a game world state, a rendered screenshot, or a structured filing. ALE composes evaluation along 2 axes. The first is comparison form. Task authors pick from a small palette, including exact or hashed value matches, structured numeric fields with tolerances, geometric surface or point cloud distances, visual appearance through a vision language model judge, behavioral world state under a fixed input trajectory, or free text rubric scoring. The second axis is composition. Per artifact, signals are combined either through what they call a gate and score pattern, where a binary precondition, like no toolpath collision, must pass before a continuous quality metric is computed, or by averaging a binary checklist. The gate and score idea is like a structural inspection before grading craftsmanship. If the bridge doesn't stand, you don't bother measuring the elegance of the welds. And critically, ALE deliberately avoids using a language model as a holistic judge wherever a deterministic alternative exists. When a model judge is unavoidable, like scoring a rendered video, the judge is given narrow, evidence-anchored yes-no probes rather than asked to vibe check the result. The agents being evaluated are what the authors call generalist computer use agents, which they decompose into 5 functional layers using a body metaphor: a brain that does reasoning and planning, eyes for GUI perception via screenshots, a body that orchestrates control flow, hands that invoke structured tools, and feet, which is the runtime substrate where actions actually take effect. The point of this decomposition is to expose how existing agent families are incomplete. Traditional command line agents, like SWE agent, have everything except eyes. GUI agents, built on vision language models, have brain and eyes but shallow body, narrow hands, and restricted feet. ALE tasks demand the union. To bring command line native harnesses up to the generalist level, the authors expose GUI operations as ordinary tools through a unified bridge, so the same model reasons over shell output and screen pixels in a single action loop. The results are striking and a bit sobering. The strongest configuration, which is Codex paired with a model called GPT 5.5, scores about 24% overall pass rate across all difficulty tiers. On the easiest tier, called Near Term, it gets 38%. On the broadest tier, Full Spectrum, which guarantees at least one task per subdomain, it gets about 23%. On the hardest tier, Last Exam, it scores 0% full pass rate, and most other agents also score near zero. For context, that same configuration scores 82% on Terminal Bench, a popular existing benchmark. Looking across configurations, the choice of foundation model accounts for roughly 3 times more performance variance than the choice of agent harness, suggesting the underlying model still dominates. Domain-wise, frontier models do best on computational mathematics and agriculture, both above 55%, and worst on education, below 25%, likely reflecting how much code-adjacent training data the models have seen versus specialized professional workflows. A failure analysis on Claude Code with Opus 4.7 shows that roughly 3/4 of failures are about understanding the domain or choosing the right approach, not about execution mechanics. Lacking specialized knowledge, agents default to ad hoc shell scripts instead of using the proper domain software, which also explains why GUI usage stays surprisingly low, even when tasks designate graphical software as the primary tool. There are real limitations to flag. The reliance on industry experts and a multi-round QC process makes the benchmark expensive to scale and slow to update, even with the living benchmark design. The 55 subdomains, while broad, are skewed toward digitally mediated work and exclude sectors where the core labor is physical. The deterministic verification, while a major strength, may understate partial progress on tasks where a near miss has real economic value. And the failure taxonomy itself suggests that current agents may be more bottlenecked by domain knowledge baked into the model than by harness engineering, which means the benchmark's signal could plateau if frontier model training continues to underweight specialized professional content. There's also a quiet contamination risk. Even with private holdouts, the public 10% will inevitably leak into pre-training corpora, which is why the rotation strategy is essential to long-term validity. The bigger picture is that ALE is positioning itself as the ImageNet moment for professional knowledge work, an attempt to give the field a verifiable, broad, realistic target that, if saturated, would actually correspond to economic transformation rather than just another benchmark line going up. Now let's walk through some questions you might have after hearing all of this. First, why insist on deterministic verification when a strong language model judge could probably score these tasks reasonably well? The author's concern is that holistic model-based judging is both gameable and noisy at the long horizon scale ALE targets. If your evaluator is a language model, then improvements to that model class can artificially inflate scores without corresponding capability gains, and stylistic features can fool a judge into accepting wrong outputs. By forcing tasks through deterministic gates, plus narrow evidence-anchored probes only where necessary, ALE makes the scoring resistant to the same kind of model drift that's evaluating it. Second, what does it actually mean that the foundation model contributes 3 times more variance than the harness? It means that if you're trying to climb the ALE leaderboard, swapping out your prompting framework or your tool layout gives you modest gains, but swapping in a stronger base model gives you much larger ones. That's not surprising in itself, but it has a practical implication. A lot of agent engineering effort right now may be optimizing the wrong layer. The real lever is making the underlying model better at sustained professional reasoning, which probably means changing what goes into pre-training and post-training, not just refining the scaffolding around it. Third, why are agents falling back on Bash and shell scripts even when the task is supposed to be done in a GUI application like SolidWorks or RPG Maker? Because the agent doesn't actually know how to use the domain software. When you lack the procedural knowledge of how a professional would manipulate a specialized tool, the path of least resistance is to write code that approximates the result. The benchmark catches this because the evaluation often requires the actual artifact format produced by the actual software, so the shell script shortcut doesn't pass the gate. This is a pretty direct signal that current models, despite massive code training, have shallow exposure to the long tail of professional desktop applications. If you build large-scale recommendation systems, ALE has a few immediately useful lessons. The first is the value of gate and score evaluation for complex multi-stage pipelines. Recommendation systems often suffer from optimization of mean metrics that mask catastrophic failure modes, like recommending policy-violating content or breaking personalization invariants. Adopting an explicit gate, where a recommendation must pass binary safety and integrity checks before its relevance score even counts, is exactly the pattern ALE uses for verification, and it maps cleanly to candidate generation and ranking stacks. The second lesson is the taxonomy-driven coverage approach. Most production recommender evaluations are heavily skewed toward the head of the content distribution, where engagement signals are dense. ALE's discipline of guaranteeing at least one task per subdomain is analogous to ensuring evaluation coverage across content categories, user cohorts, and intent types, which is the kind of thing that catches degradation in niche segments before it becomes a business problem. The deeper analogy, though, is about agentic workflows in the recommendations stack itself. As teams increasingly use language model agents to do candidate curation, prompt-based re-ranking, or automated experiment design over recommender pipelines, you face exactly the verification problem ALE is solving. Outputs are heterogeneous, success criteria are ambiguous, and human review doesn't scale. Building internal benchmarks that follow ALE's pattern, real shipped workflows from your recommendation engineers, scored by deterministic checks against reference artifacts, would let you measure whether agentic automation is actually ready to take on real production work, rather than just demoing well in cherry-picked scenarios.